fixing Hubble in the first place, but going back and fix the remaining bits and pieces.
But will you also tell us how you crossed the Atlantic with your plane? I think
Yeah.
that's
Okay.
also I'm very curious.
So, first of all, I apologize for being so late. I expected more from Switzerland, actually. When I left Tarbes, I had a very specific departure time. I had to call the tower and ask for permission to start the engine at a certain time, and then arrive at a certain point in space near the Geneva airport at a certain time, and everything went swimmingly, and I landed and taxied to where they told me to go and shut down, and then they came with the truck to tow the airplane, and they didn't have the correct interface. They basically had no tow bar. And they had tow bar for Airbus 321 and Boeing 787, but not for my little propeller-driven airplane. And so that took an hour, and some very nice gentleman came out with a big book, and he flips through the book and he shows me on page 300 where it says, "The pilot is responsible to bring his own tow bar."
No way.
So, anyway, and then I went to the rental car that I rented in March. I ordered the rental car, and he says, "Oh, I'm so sorry, we made a mistake, we have no rental car." But thank you for waiting, I'm here. And it's truly enjoyable to see Antonella. I was faculty at Caltech. I was an astronaut. I was the head of science for all of NASA, working with Alvaro Jimenez, for those of you who know him, in ISSI. But I have to say that I had the most pleasure, the most happiness for 2 years at Space Telescope Science Institute, working with Antonella, and for those of you who know Mad Mountain and the wonderful staff there. And I think it's in large part because the people who work there, and I suspect all of you, we do this because science is important, of course, but it brings us great joy. And working on the Hubble has always made me very happy. So I want to tell you, I know that there's different types of space science that you all do, and the number one reason I came, is to see the Institute and to meet all of you. That's really the purpose. But, and we flew, long ago a patch on the Hubble mission. That's with Claude and Jean-Francois Clairvoy, both of them close friends. But it's the normal thing when you come to visit an institute to give a talk. So we'll see how this goes. So because I was, a senior administrator, I was required to learn, all these things about NASA's mission. And I was very bad at that. Every time there's a new president, a new NASA administrator, NASA has to write a new mission statement. So I gave up, and my mission statement for NASA is that NASA innovates, it creates new tools to go and explore. When we explore, we discover things, and when we discover things and share it, we inspire our nation and the world. And I think this is the essence of science. And in astronomy, specifically, I think it's cool because we get to ask really big questions. Where did we come from? So where did the universe come from? Where does the visible universe that we see come from? Where does the chemical elements that we're made out of come from? And this is, these are the questions we get to answer. Where are we going? For NASA, it's, where are humans going? We think we're going back to the moon, someday to Mars. I think it's going to take a while longer than what is advertised. But also, where are we going as a planet? What is the trajectory of the climate of planet Earth? And I think, as scientists, we have a pretty good idea, and it's not a very good trajectory. What's the future of the universe? Things like that. And then finally, this last question is what I find most interesting. I think the most important question is, what are we going to do about, a warming climate? When I landed in Geneva, I was surprised how warm it is. and flying in, I did not see a lot of snow on the mountaintops. And you all know this. That's probably the most important question. I think the most interesting, or one of the most interesting questions that's now a well-posed scientific question is, are we alone in the universe? And, you know, between Kepler and TESS and Gaia, you know, we know that basically when you look at the night sky, every star has a solar system with multiple planets around it. And 30 years ago, we had no idea. I mean, you could guess, but we actually know that. We know that on Mars, there's all kinds of organics in the surface. We don't know what's below the surface, but 3.8 billion years ago, Mars was a warm, wet planet with snow-capped peaks, puffy clouds, probably a blue sky, rivers, lakes, salty seas. So those things we know from being on Mars and exploring. And 3.8 billion years ago is about the time life started on Earth, we think. Now we've traced, you know, the tree of life back to a last universal common ancestor. Mars was habitable back then. Earth was habitable. Life started on Earth, or maybe life started on Mars and we're Martians. You know, we have no idea. So perhaps Mars is a place we might find out if there's life. It could be the same life as Earth because we exchange things. Europa and Enceladus are possible places in our own solar system. There could be life. And I think we are 25 years away from having a space telescope that can look at sun-like stars with Earth-like planets and do spectroscopy of their atmospheres and see if there's any, you know, maybe a dozen or so planets that we'll be able to interrogate to see if there's any place just like Earth. I think you already know that with the last 50 years of astronomy and space astronomy, that we've been able to tell the story of pretty much the whole universe. Pretty much the whole universe from some event, and when matter and energy were decoupled with the cosmic background radiation, and the expansion of the universe, and now the acceleration of the universe, formation of stars, galaxies, structure in the universe, the Earth. Pretty amazing that we can tell this whole story. And with Hubble, we've been able to observe in detail back to about 400 million years. And James Webb is going to be able to really fill in the story of what happened very, very early on. I like to think of it as if your parents give you an album of pictures of your life when you were young. And you open the book and you say, okay, I have a picture of my mother, and she's pregnant, and then a picture of me as a 4-year-old, but what happened between? What did I look like? What did I do? And they go, we don't know. We don't have any pictures. And that's what we have of the universe. We have, you know, the universe as it was a toddler. We have kind of a birth picture, and James Webb is going to help us fill that in, and many other things. I think you know that the Hubble Space Telescope was named after Edwin Powell Hubble. You know, he looked at these fuzzy images, saw Cepheid variable, and at that time they actually didn't know really that these were clouds of stars. They thought they were nebula, but when they started seeing familiar things, this is sort of the discovery image. You can see variable. There's a star there. He was able to measure the distance, realize it was at great distance, and by measuring many such galaxies that the universe is expanding. Now we have Photoshop, so this looks more familiar than a glass plate, but this really kicked off the era of astronomy and such that we named Hubble after Edwin Hubble. Now the Hubble Space Telescope is not a particularly large telescope. It's a 2.4 meter mirror. It's the size of a tour bus. But a couple of things that are, you know, very important about it. One, it's above the atmosphere, so the stars don't twinkle. We get clear view. It can see ultraviolet light, and from the visible ultraviolet to the near infrared. And so we can see light that doesn't make it down to, say, the European Southern Observatory. But also it doesn't have, gears and drive motors turning the telescope. You can observe continuously. You don't have day and night. And so Hubble really is a unique partner to ground-based telescopes to be able to see much more clearly. When the Hubble was launched, it was the first of the NASA Great Observatory program. And it turned out when it was launched, it was an okay telescope, but it was not a great observatory. If you remember the story, or you don't know the story, when it was launched, it had a beautiful mirror. Perkin-Elmer crafted the mirror, the best technology available, very smooth, diffraction limited in the ultraviolet, very hard to do. But they built it to the wrong shape, very slightly. Just a few microns at the edges of the mirror was too flat. It's not important what the reason is, but as a result, when it was first launched, people made a lot of fun of the telescope. There were comics, there were Johnny Carson made fun of NASA. The moon looks like a potato maybe, and Jupiter wavy, Saturn's rings, and very angry taxpayers, not just in the US, but also in Europe. Of course, the European Space Agency was a large partner in the Hubble Space Telescope. But the other feature of the Hubble Space Telescope that's very important, it was built to fit inside of the space shuttle, but also it was built to be serviced by astronauts from the space shuttle. So it has doors, and it has interfaces for people wearing bulky gloves. And so in 1993, a crew of astronauts went up to the Hubble and were able to put in corrective optics. Basically, their contact lenses is what some people describe it, but they're mirrors. Because we could observe very bright stars and precisely measure the shape of the wavefront, it was very easy to determine what the prescription of the mirror is and then invert that to get the correct prescription. In fact, Hubble has better optics now, in part because of the mistake, than it would have if we had launched it and not done anything, because we were able to correct the actual on-orbit performance. And then every other mission since then, we did 5 missions, we put up new instruments. If you think about what kind of camera was in your cell phone in 1990, I can tell you, none. It didn't exist. We didn't have any kind of commercial CCDs. CMOS imaging sensors hadn't been invented. People used image tubes and these strange old technologies. So in 1990, the instruments were very primitive. But starting really in 1997, we started putting up modern detectors, better detectors than were available at most observatories, in fact, because the Hubble program had the money to pay the developers to build those. My first Hubble mission was in 1999, this one with Claude Nicollier and Jean-Francois Clairvaux and crew. And we put in new gyroscopes, so we fix things that break, we fix things that wear out. We put a 486 computer in, Intel 486, which is running the Hubble today. At that time, it was rather advanced, and some other things. And then in 2002, I led a mission where we really did a complete renovation of the Hubble. We put new solar arrays, we put new thermal systems, we put the advanced camera for surveys with a 16 megapixel camera with both a wide field imager and a narrow field imager with great ultraviolet performance, and changed the power system as well. And then in 2003, we lost Space Shuttle Challenge Columbia. And it was decided not to go back to Hubble anymore. I was NASA chief scientist, and so I did everything I could to keep Hubble alive. And then in 2006, after we had returned the shuttle to flight, a different administrator said, if we're going to fly the shuttle, we should do it for important things. We're going to go back to Hubble. And so I got to go back to Hubble in 2009, and we put in an ultraviolet spectrograph, a new wide field camera, and repaired the advanced camera for surveys and STIS, plus new batteries, new gyros, a bunch of other things. So Hubble, remarkably, even though that was 2009, today everything is working on Hubble, everything is still, observing. And as an example, the Wide Field Camera 3 has a 16 megapixel visible detector and then infrared detector. We actually flew a prototype of what was going to fly on James Webb and the electronics. So we have an infrared channel. I'll show you something from that. But the Wide Field Camera 3 is already more sensitive than will be the 38-meter extremely large telescope from the European Southern Observatory. Okay. Now you should be skeptical. I mean, a 38-meter mirror. But, one, Hubble is above the atmosphere, so there's no noise from the atmosphere. And I was very careful, sensitivity, so signal to noise. And those detectors are essentially noiseless. Less than 1/3 of an electron noise per well in those detectors. They're just superb. And so if you have no noise, then your signal to noise is very high. And they will obviously be partners. We'll see things with the ELT and then use Hubble and James Webb to follow up. And Hubble and James Webb will see things and we'll use the EELT to do spectroscopies, for instance. In the end, all programs are about people. In 2009, this is the crew that went up to the Hubble. I'll be very quick, but this is Scott Altman. The commander, he flew 4 missions. This was his second Hubble mission. I flew with him in 2002. Megan MacArthur was our flight engineer and robotic arm operator, the Canadarm. She's an oceanographer. Greg Johnson was our pilot, or co-pilot. His first flight, he's an aerospace engineer. That's me, I was on my 5th flight. Drew Feustel is a geologist. He was my spacewalking partner on his first flight. Mike Good on his first flight, an Air Force pilot. And Mike Massimino on his second Hubble flight also, and he's a mechanical engineer. So we had 2 shuttles, Atlantis and Endeavour. Endeavour was there to rescue us.
All right, let's go!
We wear pressure suits in case we have to jump out, which is pretty absurd. We had to go to the right vehicle, Atlantis. We also wear parachutes, same thing, in case we have to jump out. It's rather cramped in the space shuttle. Megan was the last one in and closed the door.
It's a great day to go fly. On behalf of the KSC Processing and Launch Team, I'd like to wish you, your crew, and the whole Hubble Space Telescope team a great mission. Good luck, Godspeed, and we'll see you back here in about 11 days.
It takes about 10,000 people to get a space shuttle ready to go. A very large team. We like this liquid engines first. Once the solid rocket motors, those cylinders on the side go, the shuttle is going to take off no matter what. It's a very violent ride. This is not a smooth thing. For the first 2.5 minutes, we ride on the solid rocket motors. They separate. We have cameras on all of these, so the shuttle on liquid hydrogen, liquid oxygen engines continue on. You'll see it there in a moment. So that bright dot is the shuttle continuing on. After 8.5 minutes, all the fuel is depleted, so we throw away the tank. And it's interesting, once we get to orbit, we open the payload bay doors. Inside of the payload bay doors are Freon radiators. That's how we reject heat. And this is all of the equipment we've brought up to service the Hubble. If you look at the fraction of mass reused, this is the most reusable spacecraft ever built. Much more than a Falcon 9, for instance. And we flew we launched 135 times. Sadly, we lost 2 vehicles. But much of what was done on the space shuttle is why SpaceX was able to develop a reusable vehicle. once we got to orbit, I was able to put on my spacesuit, and this is when I'm truly happy. It's when I'm in a spacesuit and out working in a vacuum. The spacesuits are really amazing. They're cloth suits, about 11 layers, one of which is rubberized. And inside is 4.3 pounds per square inch of pure oxygen. Outside, of course, is a vacuum. The backpack has oxygen, batteries, lithium hydroxide, which absorbs carbon dioxide, and a cooling system. We actually have an evaporator that evaporates water to space, and those hot molecules help cool the suit. It's a very analog suit. You know, we don't have like heads-up displays and the things you see in science fiction movies. All of the tools have to be tethered. So this is my tool belt, and you can see the Earth reflected in my visor. We have lights, and these are cameras. So you'll see some of the views from my head. That's the Space Shuttle wing. And anyway, so almost all the time in space I'm smiling. Yes?
Sorry, I am always surprised when I see this, 11 layers, all these things, so look like, quite big, And then you see this, SpaceX astronauts and tourist astronauts almost with a Giorgio Armani suit. What is the difference between these modern astronauts to...
Because those are costume suits, basically. Those are designed that if there's a leak in the capsule, they will survive. But they can't move, and only for a very short period. They're the modern version of the orange suits that you saw us walking out in. And if there's a leak in the capsule, those suits, you'll be the Michelin man. Unable to move your arms and legs, but you'll survive for a short period. Whereas this is a suit to go out and work. The idea is that in the SpaceX capsule, if there's a leak, there will be some pressure for some period of time for them to come back down and splash in the ocean. Where here, you have to be able to stay in a vacuum for, as much as 12 hours. So to give you a sense of scale, that's me with the red stripes and the Hubble Space Telescope. So we grab the Hubble with the robotic arm and put it into the payload bay, and that allows us to work on it. Now this is Drew Feustel, and this is the old camera that was put on in 1993, the one with the corrective optics. And at this point, it's one of the few times I was not smiling, because Drew put the wrench on the old instrument and went to turn it, and the bolt was stuck. And it was designed so that if the bolt ever got stuck and you put too much torque on it, the shaft would break and the old instrument would stay in Hubble forever. So that's why I wasn't smiling. And so finally, after a lot of discussion with the experts on the ground, they said, what are we going to do? And there's nothing left but just try it. And we had torque protection, but with all of that, it wouldn't turn. So finally, we took the torque protection off. Drew gave it one mighty pull, and suddenly it rotated quickly. And I was still not very happy because either it came loose or it broke. But finally, we put the power tool that spins it quickly, and I saw it moving out. And then I smiled again. So, to give you a sense of what it's like to do a spacewalk, as I said, Hubble was built with doors. So you release some bolts, you open the doors. The Hubble instruments are quite large. This is one of the old instruments. This happens to be the Corrective Optics Space Telescope Axial Replacement COSTAR, the original corrections, about the size of a commercial refrigerator, roughly 400 kilograms. But fortunately, it has inertia, but it's very easy to move because everything is in free fall. The other thing we did for the first time is repair an instrument in space at the board level. in the spacesuits. And it involved taking out tiny screws. So to take out tiny screws, you need a tiny screwdriver. Actually, I released the torque on each of the screws to make sure none were stuck, and then used a small screwdriver to remove them all the way. And this fancy plate is to make sure none of the screws are lost. If you look very carefully, you can see the tiny number 4 screws floating around. And then the cards, of course, are standard cards, but they're very sharp. So to remove them, they wouldn't let me touch them. I had to use a special tool. So I removed 4 circuit cards. We put 4 new cards in. A power supply had failed and fried all the cards, so we had to replace those. And that was to replace the advanced camera for surveys and bring it back to life. That's the Baja Peninsula, and we're coming back in. And this task we were told not to try. You know, we had review boards and senior people and the NASA managers, and in preparing for the flight over a year, they said, we think it's a waste of time, there's no way you will succeed, it will take too long, something bad will happen to the telescope. And I persisted, because this is a very important tool for science, the advanced camera for surveys. And so you can see I'm very happy, because it was successful. And when I was walking out to leave Houston, usually there's a few managers there to say goodbye. And one of the people who was not in favor of us doing this task, I got to him and I said, 2 hours and 30 minutes. He goes, what? I said, 2 hours and 30 minutes. He said, what's that? And I said, that's how long it's going to take me to repair the advanced camera for surveys. He goes, yeah, sure. 2 hours and 32 minutes. So I was pretty happy. And when I first showed, after the flight, we did a very large presentation, and I said, this is the happiest I've ever been in my life. And then I realized my wife was in the audience. So I said, this is the 4th happiest I've ever been. The first is when I married my wife, my first child, second child, and then this. So, anyway. So we did a lot of other repairs on the telescope. We fixed another instrument. We put in new batteries, new gyros. We put in a new fine guidance sensor. We put new insulation on the telescope so that it would stay cooler. The telescope was starting to heat up because the space environment was degrading the blankets that were launched originally. And finally, we lifted up the Hubble and let go of it, and off the Hubble went to do its mission of astronomy. I mean, to me, one of the amazing things is Hubble has been up there for 33 years, and it's now still state-of-the-art. And there just aren't other spacecraft that are like that. You know, the closest would be the International Space Station, that's had many, many visits, but even the station is not doing the kind of science that Hubble does. Fortunately, once we got rid of the telescope, we could all relax and have a meal. I like to hang upside down. We make sandwiches with tortillas because bread makes too many crumbs. It would fill the cabin with a snowstorm. So that's a chicken sandwich. Most of our food is in pouches. That's a shrimp cocktail. And we have all kinds of other horrible food. My son, who at that time was about 10 years old, asked me to film a ball of water, take a picture of a ball of water. And of course, you know, being a physicist, a ball of water is a convex lens. It inverts the image. So I asked Drew to get behind it, and it also magnifies the image. His nose is not that big. And then I said, get very, very close, you know, like a magnifying glass. And the cool thing is, at some point, just a bit of the water touched his skin, and then surface tension, you know, causes it to spread out, you know. One of the most fun things to do is look out the window of the shuttle. This is obviously while we still had the Hubble. You can see that outside protection, thermal protection, is deteriorating. That used to be a clean NASA and most of it's broken. You can see a little tear there. This is the Cape Verde Islands off the coast of Africa, and the wind is blowing this way over those islands. And for 100 kilometers, you can see, you know, the swirls. It's, you know, lots of interesting things that you can see. Sometimes you see just from the density variations and the condensation of the clouds, you see these very, very long waves. And the weather folks call them gravity waves, but it's Kelvin-Helmholtz instability due to shear. So it's very interesting. Sunrises and sunsets, for scale, that's 100 kilometers, 105 kilometers roughly. You can see if you look very closely some clouds. And of course, you know, we survive in the first 5 kilometers. So very pretty. I'll come back to this picture a little later. I happen to know that's a sunrise because the sun is just much too bright to look at. And so the strategy is you position yourself at the window before the sun comes up and you just start clicking, you know, once a second or so, and then you can get a picture like this. Because if you wait for the sun to come up, it's, you know, it's too bright. We had very bad weather in Florida, so we had a couple of days just to play around. This is in the middeck. Those are M&Ms. That's orange drink. And after the flight, we said, what kind of orange drink? And they told us it was Tang. So we actually do fly Tang. A ball of water being eaten. We did some serious physics. This is the stability of rotation about various axes and conservation of angular momentum. We actually filmed this for a class so that they could use that. It's very small in the middeck. On the flight deck, Scott Altman and Ray J and Megan, Greg Johnson, were playing video games. This is actually a Linux machine. I helped develop the software. It's a flight simulator so that Scott Altman could practice landing. And we have all the data. For 12 days, he had not flown the space shuttle practicing to land. We have aircraft that he would fly, and so very important to do that. And finally, after 2 days, they said, okay, weather in Florida is bad, go to California. Scott put his California music on, and Megan said, get to work. So then around 8,000 kilometers from California, we did a very small burn to slow down. That allowed us to start entering the Earth's atmosphere. It's about 2,000 degrees C outside of the shuttle. We have carbon on the bottom of the space shuttle and ceramics that absorb the heat. We just slam into the atmosphere to slow down, and we're a glider for that entire 8,000 kilometers. Here we're coming into land at Edwards Air Force Base. We're doing over 300 kilometers an hour, going through about 3,000 meters, 21 degrees down, nose down. At 100 meters, we put the landing gear down, and Scott Altman, you know, flew us to a beautiful landing. So we spent about 2 weeks in space. We did 5 spacewalks. We grabbed the Hubble, we let go of the Hubble, orbited 197 times around the Earth, about 8 million kilometers roughly, 5.3 million miles, but no frequent traveler miles. And rolled to a stop, and of course the big question is, do the new instruments work? And so this is an image from one of those new instruments. This is a cloud of gas and dust. This particular image is taken through filters of oxygen, nitrogen, sulfur, and hydrogen. And they're all combined into one image. And inside of this cloud is a baby star. It's maybe 10 million years old. It's a Herbig-Haro object. And that just means a young star where we see jets of material coming out. You can see a little bit of a jet here, a little one there. The reason, much better. The reason why we can see this is because there's some young stars and a lot of ultraviolet light, and these stars are energizing this gas, causing it to glow in the colors of those ionized atoms. And eventually, this star will produce enough solar wind to blow a bubble. And so between being evaporated from the outside and a bubble in the inside, eventually, 50 million years, we'll be able to see the star. And this is with the new wide field camera. And this is basically a stellar nursery. It's what we looked like 5.5 billion years ago, our solar system. And I mentioned that we put one of the infrared channels that would fly on James Webb here from NIRCam and the electronics. And the size of the dust, the silicates, neon magnesium silicates that keep us from seeing inside are about a micron. And so if you had an infrared camera with a wavelength of a micron or two, the light could get out. And so this is that infrared channel. So now we can see that baby star, and we can see the jets. And that goes to the outline still of the nebula, and stars right through it, background stars. And so this is the new capability. So this told us in 2009 that James Webb NIRCam would work, which was a big deal. Now the other thing I think you know Hubble does, besides taking these beautiful images and studying star formation and the area around black holes and galaxy formation and things like that, is these very deep fields. So this is an ultra deep field. It represents weeks of exposure. And in this image, every single dot, so if you were to come to the screen with me and just pick a dot, that dot there, that's not noise, that's not a star in our galaxy, that's a galaxy with 50 billion to 200 billion stars. And some of them that are very red are very, very distant. They're redshifted by the expansion of the universe. That particular galaxy set the record up until James Webb at around 400 million years old. So we knew that by 400 million years after the Big Bang, the universe is 13.8 billion years, that stars had already assembled themselves into coherent structures, galaxies. And the question is, what caused that organization? We know from the background radiation that there were fluctuations in the radiation such that the universe wasn't perfectly smooth. So we would expect the hydrogen and helium to collapse in such a way that it's also not smooth. But we still don't know if dark matter caused the kind of assembly of galaxies that we now see in the universe. It may have been primordial black holes, that the gas collapsed and produced very large, massive black holes, and the gravity of the black holes is what caused other matter to start forming stars. So James Webb is hopefully going to tell us that. But when Hubble was designed, we thought we might be able to see back, 6 billion years, roughly. And here we are probing the very early parts of the universe. But what I think really distinguishes Hubble from every other observatory previously is that many people had a view of the universe that it's, you look up at the sky, it's a bunch of points of light. And with ground-based observatories, even very good ones like Palomar, there are some fuzzy images of galaxies and other interesting things. But for the first time, Hubble has given us views like this. This is the Great Nebula in Orion. So in the constellation Orion, which we have the 3 stars in the belt, the 3 stars in the sword, of course the shoulders and the legs, the middle star in that sword is actually this nebula. So we can see it with our eyes. But Hubble has shown us with the same kind of resolution that we have looking around our world. This is a 16 megapixel image. That the universe is much more diverse, rich. It has texture and fabric and beautiful color. And what you're seeing here again is gas and dust. And we've even been able to make, using modeling, but a 3D fly-through of this. As if you're on the bridge of the Star Trek Enterprise, flying through. It's phenomenal. But there are, hundreds and hundreds of baby stars that have been born inside of this cloud. Some of these are probably, examples that have made their way out. And it is, I think it's just, looks like a work of art. Now switching gears a little bit, who is the James Webb Space Telescope named after? We know Edwin Powell Hubble, famous American astronomer, James Webb was an administrator, a NASA administrator. Before that, he was at Office of Budget. And before that, in the State Department in the U.S. But he was the NASA administrator from about 1961 to 1967, that critical period where we were developing the Apollo rocket and the capsule and the moon lander. In 1967, a new administration, new president came on board and selected a new NASA administrator, so he didn't get to stay for the moon landing. So he's best remembered for managing, the very rapid development of NASA with NASA centers around the United States, the Gemini program, the Apollo program, and preparing for landing on the moon. But what people don't know about James Webb is that he was very forceful with a guy named Jerome Wiesner, who was the president's science advisor, and President Kennedy and President Johnson, very forceful that the foundation of NASA should be science. And so he's the one that really cemented that into the NASA framework. We already had science, we had various probes and things, but he made sure that it would have lasting value. And so for that, the NASA administrator that I worked for in 2003 and 2004, Sean O'Keefe, named the telescope after James Webb. I was surprised at the time, but once I read the history, it kind of makes sense. Now, I think you know that in the US we do decadal surveys. In ESA there are vision documents. And we had decadal surveys that said after Hubble we should build an infrared telescope to see the very early universe and other things. And astronomers tend to be very cheap. And so they thought, well, the most we can probably afford is a 4-meter telescope. And so they were, that's what the decadal survey recommended. And NASA Administrator Dan Golden, when Alan Dressler presented that, said, all he wants is a 4-meter that goes from half a micron to 20 microns. And I said to him, why do you ask for such a modest thing? Why not go after 6 or 7? And because he also makes the funding decisions, that opened the door for us to actually plan on a 6.5-meter telescope, roughly. And without Dan Golden, we'd have a 4-meter. It would be a good telescope, but not like James Webb. James Webb, I think you probably know because it's already been up there doing these things, but we were going to look at the very high redshift universe, the very first stars and galaxies, to try and understand better gravitational lenses and the black holes and mass distribution that causes them, which is mostly dark energy, to look at the birth of stars and protoplanetary systems, and specifically to look for molecules that are the precursors for amino acids and proteins and life, and to watch these star systems as they grow. We now know that when stars are formed, the planetary systems form at about the same time. James Webb is not like other telescopes. It is an open design. Light comes in, hits the primary mirrors, secondary mirror, and into the instruments. There are 18 segments. Is that right? Yeah, 18 segments. One's missing in the middle where the secondary goes. And the mirrors are made out of beryllium. And that's because this entire structure is cooled passively, just radiates to the universe to about 38 Kelvin, 40 or 38 Kelvin. And that's because it's an infrared telescope. If it were a room temperature telescope, the telescope, just black body radiation, would produce enough light that you wouldn't be able to see these distant infrared objects. So the beryllium mirrors are 1.5 meters across. They're machined at room temperature. And you have to machine them so their shape is wrong. So that when you cool them and they shrink a little bit, they warp to the correct shape. So this is a map. You can't really see the units, but the full scale here is about 40 nanometers. And so this shows distortions in the mirror that would make it a very bad mirror. at ambient temperature, 21 degrees C, and when it's cooled to 40 Kelvin, this scale is only about 10 nanometers full scale. And you can see that it's very, very smooth. A couple of little things here. And we thought we'd have to do many iterations, but it turns out the first time that Ball Aerospace made them, they were all, within requirements. Now, one day I asked, somebody was telling me how smooth they were in a meeting. I was now in charge of the James Webb program. And they said, oh, these are, so many nanometers, and they're the smoothest mirrors we've ever built. So I thought, well, what would happen if you stretched one of those mirrors to the size of the United States? How big would the mountains be? In the United States, we have 4,000-meter mountains. But I'm in Switzerland, so if you stretch one of those mirrors to the size of Switzerland, the mountains are 1 centimeter tall. And of course, you have Mont Blanc, which is 5,000 meters. So that's pretty smooth. And then I said, well, what happens if a E. coli bacteria falls on the surface? It's much bigger. It's the largest object by 2 orders of magnitude on the mirror. And there were many bacteria that fell on the mirror. I think they're dead now, but. So we tested the mirrors in vacuum chambers. We tested the whole assembly to make sure we didn't have a problem like Hubble, and all is good. You've probably seen this. James Webb is at the Earth-Sun Lagrange 2 point, 1.5 million kilometers away from Earth. It's semi-stable, it's very cold, it's dark, and James Webb has a big sunshade the size of a tennis court to block the sun from the telescope side, and we had to deploy that. It was launched with an Ariane 5 rocket, a very beautiful rocket. And so this shows you the deployment strategy. And there were about 300 steps, and if any one step didn't work, the telescope would be lousy. It would be basically broken, and no astronomy. 5 layers, SPF 1 million. If you had sunscreen of SPF 1 million. After the sun shield deploys, there's actually a little rudder for solar wind. The secondary comes out, the side comes out, and then actually the telescope extends up a little bit. I'm amazed that everything worked just right. I mean, really incredible. I think we're all amazed. This is just another way of looking at it. So all of this is the cold side. The sun is blocked by these very thin Kapton and Mylar layers. And then the spacecraft with the solar arrays, the pointing gyros, the thrusters, the communication system, computers and such, is on the warm side. And so James Webb can't look at any place in the sky. It depends on the season, because we have to keep it oriented so that this stays on the cold side. There are 4 instruments. We have a near-infrared camera. We have a near-infrared spectrograph, near-infrared beam from half a micron to a few microns. We have a mid-infrared imager, and we have a near-infrared imager and slitless spectrograph that also doubles as the fine guidance sensor. I think I don't have to explain too much, but this is the Voyager image of the Earth. This is dust in our solar system. And, these are some of the kind of things that you can do. This is a simulated spectrum of the Earth, and actually it looks very much, when we look at the moon in reflected light, we can reproduce this. And, there are many lines from oxygen and water vapor. There are lines from carbon dioxide, lines from methane. There's a general jump here when you hit chlorophyll, because we have so much vegetation on Earth. And this is the region that James Webb studies, basically out to about 20 microns. James Webb was launched on Christmas 2021 by an Ariane 5. Pretty amazing that in the middle of COVID, we had all these people that were able to support it, finishing the spacecraft, mating it to the telescope, getting it to Kourou, launching it. with 3 space agencies, NASA, the European Space Agency, Canadian Space Agency. And James Webb was designed with a requirement of 5 years of lifetime, which was driven by propellant. We believed that by being very efficient in operations, we could maximize that to 11 years. James Webb needs propellant for 2 things. One, to desaturate the momentum in the reaction wheels, or actually control moment gyros. And the other is to station keep at Earth-Sun L2 at the Lagrange point. It's semi-stable, it's a saddle point. And we needed a lot of fuel because between the injection from Earth orbit to L2, we had correction burns. So the big rocket, is not very precise, and so we needed to use fuel to make adjustments, to speed up a little, to go this way or that. And the Ariane 5 was launched so perfectly that we used almost no fuel for those corrections. So now we think we might have even as much as 30 years of propellant, which is the limiting component. All right, so you get to orbit, you align the mirrors, and you take a picture of a bright star to see if it works, and to make sure that no mistake was made, and we have a blurry image like Hubble. And everybody was just blown away by how wonderful it is. The requirement on the telescope was to be diffraction limited at 2 microns. And in fact, the optics are so good we're diffraction limited at 1 micron. Turns out that's a big deal for what we're going to be able to see, especially for things like imaging exoplanets. But what's also interesting, so Hubble, the secondary mirror is held up by a cross. And so Hubble images have those diffraction spikes in a cross. Of course, James Webb has diffraction from the tripod, but also because each of the mirrors is a hexagon, we have hexagonal diffraction. So when you see bright point-like objects, stars, you'll see the characteristic 6 points from that. But what's really amazing and was a very happy moment is, this image was 30 minutes. And in the background, we're already starting to see galaxies. All of these things in the background, those are galaxies. And, we should have anticipated that a short exposure would start bringing up galaxies, but it's a big telescope. It's a 6.5 meter telescope. And so in that 30-minute exposure, we just see, you can actually start making a catalog of galaxies. This alone, when I was a graduate student, would have been probably 6 PhD theses. All right, so just a few comparisons. This is, one of my favorite images. It's a Hubble image taken in 2021 of Jupiter. I always love it when we study the solar system. I'll tell you about my science at the end briefly. And then here's a James Webb with NIRCam. Of course, even the Hubble images are in a sense false color. We have to assign ultraviolet to a color we can see. And the folks at the Space Telescope Science Institute who put the images together, they're taken in filters at different times, and then you combine them for Hubble. And for James Webb, we're assigning different colors, so it looks different. Obviously, this is not an infrared image. It is taken in the infrared and converted. But you can see things that we don't see in Hubble in the visible. You have to go to the ultraviolet. This is the thermal glow from a northern hemisphere Jupiter aurora, southern hemisphere Jupiter aurora. And if I were to flip back and forth, I won't do that, but you can do that at home. You can see that we're seeing into different depths of the features on Jupiter because of the wavelength range. And if you blow up the image, you can see more of the aurora. You can actually see the magnetic footprint from Io, which is way out here. You can see some of these smaller moons, very small moons, like tens of kilometers, and rings around Jupiter. Some iconic images. This is the Karina Nebula with Hubble. And so again, a star-forming region. Inside of these blobs in the middle is a baby star. Here's one that's starting to emerge. Remember how I told you it blows up like a bubble? this gas is being evaporated, and it's blurry not because the Hubble can't see well, it's because the gas blurs the star images, but still, there's the James Webb image, so that same blob, and you can see the hexagonal diffraction. And so, as I mentioned, with the infrared we can see into the area where stars are being formed. So again, Hubble image, and then the James Webb. So we're actually able to see that baby star that's blowing out. And then in the mid-infrared, we can see even further in with James Webb. One of the things when James Webb was designed, basically the 1990s, is prior to 1995, we had no knowledge of exoplanets. And so all of the design decisions were made not thinking about studying exoplanets. But we got lucky. It turns out if you wanted to do spectra of atmospheres of exoplanets, you would build James Webb Space Telescope. So we got very lucky. This is WASP 39b, so the 39th planetary system found by the WASP system, and the second planet in that solar system. I think you know the way that we study transiting exoplanets and atmospheres is when the planet goes in front of the star, some of the starlight is blocked, and so we see the intensity of the starlight go down. And when the planet is in front of the star, some of the light, so in this region, is absorbed by the planet's atmosphere. So here's an actual eclipse curve from WASP 39b. So the planet is away from the star, the planet is eclipsing the star, and then it goes back out. And in that bottom region, in different colors, different amounts of the starlight is absorbed in the planet's atmosphere. So I want to go back to this picture. So we're observing at 100 light years away this picture. And all of that light difference in the bottom of the transit is light absorbed in some very thin planetary atmosphere. Just like this, we see different colors because different amounts of light are scattered and or absorbed by our Earth's atmosphere. Now with Hubble, we've done this with WASP 39b. The blue line is a detailed model of the planet's atmosphere with hydrogen and helium, with sodium, potassium, water vapor, and CO2. And this is the best signal to noise we're able to get with Hubble. And it's suggestive, certainly of sodium. The model underestimates the amount of sodium. And we see some signals from water vapor. I would say this was exciting because we see water vapor in the atmosphere of another planet. Spitzer data does not support necessarily CO2. I mean, I would say it was said this is a CO2 peak. Maybe it's noise, maybe the model's wrong. But James Webb is the machine to do this. James Webb is a spectrographic observatory, much more so than Hubble. And so this is a similar model. This is one of those CO2 peaks, and this is the dots with the error bars are the James Webb data. And so we're going to be able to study hundreds of planets' atmospheres with James Webb and find out what's in their atmospheres. James Webb is also a great partner to the Atacama Large Millimeter Array. ALMA has produced a lot of disks around stars that have just formed, and we're starting to get catalogs of how those disks indicate planets are forming. This is an image of Foilhot taken with James Webb. It's a nearby bright star. It's so bright that it saturates the James Webb detectors, so it's just gone from super white to black, but it's not so bright that you see the diffraction spikes. And for the first time, we're seeing a lot of detail in rings, which are basically, that's 80 astronomical units. So our Earth is sort of buried, in the middle here. But further out, we can see there's probably an asteroid belt, and this is sort of the equivalent of the Oort cloud in our own solar system, gas and dust. And the fact that there are gaps, and a gap there probably means that a planet is forming or has formed and is starting to sweep out and remove that dust. If we look at this outer ring, we're actually tracking what's probably a planet in formation. This is still just dust, but it's traveling around at the orbital velocity of this ring. So we're going to be able to study that. So coming a little closer to home, James Webb is starting to look at the planets in our solar system, the moons of those planets. This is Titan in different bands, so we're able to see color bands. And we're able to see the surface, resolve the surface. There are deserts, there are ethane lakes, and we're able to look at clouds. Of course, Dragonfly, a mission that has some ESA contributions, but is a NASA mission, will launch later this decade and get there in about 2034. And it's a quadcopter, so it's going to land, do mass spectrometry, and then take off and go somewhere else. We think Titan is a model of what the Earth might have been like 4 billion years ago. One of the really exciting measurements that was just made recently as part of the Guaranteed Time Observing Program of the solar system is of Enceladus. When we went to Enceladus with the Cassini spacecraft, this is a real photo of Enceladus, and we saw plumes of water coming out of the South Pole. Cassini flew through that water, and with its mass spectrometer, saw water vapor, saw hydrogen, saw various organic molecules, and Frank Postberg recently published a paper that says we also see phosphorus, and we've seen sulfur dioxide. So we see carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, which are all the molecules that we need to make the organic molecules that we're made out of. Things like the lipid layers of our cells, RNA, DNA, amino acids. And when James Webb looked at Enceladus, all of which is in this one pixel, we see that not only are these plumes, which are a few hundred kilometers, this is 1,000 kilometers. And these plumes are not bound. Enceladus is just too tiny. That water cloud actually is huge and is actually filling a whole ring. This is now an image with James Webb, but it's filling a ring around Saturn, the E-ring. And so here's that picture, here's the plume. And if we do spectroscopy in the torus, the red line, we see these water lines. The green is right in the center where Enceladus is, and this is in the plume. So we're going to be able to study this and hopefully see if any of the organic molecules survive in the plume as well. But what I'm most interested in is Europa. Europa is not a tiny moon. This is an image of Jupiter. It's a raw image. This is Europa. It's so bright it's saturated. But Europa is the size of our moon. It has a 30-kilometer thick, maybe 5 kilometers at the thinnest, 30-kilometer thick icy shell. And then an ocean of salt water that has twice as much water as our own Earth. It has a rocky core, and its mantle is, and the core are kept molten by tidal squeezing from Jupiter as it orbits. It's got a very slightly eccentric orbit, and as a result, that core will be squeezed and heated, and that's what keeps the ocean molten. It's about 130 degrees Kelvin on the surface, and probably right around 0 in the ocean. The other thing about Europa is, if you look at the surface, there's a crater, but it's got very few craters. So the surface is very young, less than 50 million years old. So that means there has to be some mechanism that resurfaces it. And you can see all these cracks in the ice. So it's possible that there's sort of ice tectonics. It's also possible that there are plumes on Europa, and that those plumes put water out, and because Europa is so large, the plumes would be bound. They'd only go up 200 kilometers and then come back down. The red is believed to be salt from the salt water, and when salt is irradiated by electrons, it turns red. It alters the crystal structure. So this is I already described this picture, but we're building a mission called Europa Clipper. to go there, and it will fly around and study the ocean and take images and do thermal imaging and a neutral ion mass spectrometer and a dust gas spectrometer. The work that I've been doing with a fellow named Bill Sparks at SETI Institute, he was at Space Telescope Science Institute, is observing Europa with Hubble, with the Space Telescope Imaging Spectrometer, and we have a particular technique that we've used that gives the highest resolution that Hubble can achieve. And this is the image from Galileo, which flew by Europa, and we see evidence of plumes of material. We can't identify what that material is. It's probably not Tang. It's almost certainly water, but we see in a few epochs in the same place this evidence of water. In looking at ionized hydrogen and oxygen, other teams have seen a large plume, a large cloud of ionized oxygen and ionized hydrogen. Must have come from water in this same region. We see it in various epochs, but sometimes not. And so it's not clear, and these are all in the same orientation. So these dots are where we have images, and here's an example of times that we've got more than 6 sigma detection. Here's some examples. This is the most recent data that we have in hand, and there's still evidence. And what's, I think, important is it's always in the same place. And it turns out that if you look at the map that Galileo made, it's in the vicinity of a crater called Powell, one of the few craters, a very large crater. So it's possible that that asteroid hit Europa and caused a great crack, and that ocean water is leaking out. When Galileo flew by, it flew just a few hundred kilometers over Europa at this location. Now, they didn't have a way to see with a mass spectrometer, or they didn't use it when they flew through because they didn't know they should be looking, but the plasma instrument and the radio instrument saw signals that are consistent with flying through a plume of water. They went back 15 years or 20 years later and looked at their data, because after we published this, somebody said, I remember when we flew by Europa, there was a strange signal in the plasma instrument. They went back, reanalyzed it, and in fact, it's coincident with this. And then this is what James Webb can do, in principle. Now, James Webb has observed Europa, but not this side, where the plume is. So they would have been unable to see it. But if James Webb sees the plume, and it's like the plume on Enceladus, we'll be able to do spectroscopy of the water in the plume. And so we'll see a big water signal. And if there are organics, in principle, we should be able to resolve those and do spectroscopy. With a team, I put in a proposal for cycle 2, the current proposal cycle, to do this work. Unfortunately, there were 3 groups that proposed it. They were all rated excellent, but somebody else got this. But I think within a year and a half, we'll know the answer, and that's what's really important. And the most important thing is, this is a James Webb picture of the Eagle Nebula, the pillars of creation. We're just getting started with James Webb. Who knows, with this incredible capability, what we'll be able to discover. So with that, I will stop. Thank you. Of course, all of these images are on the web.
Thank you, John. This was fascinating, and it never gets tiring to have you telling the story of the launch, and it's just so amazing. So, questions?
How is it possible to align the mirrors of James Webb to a few nanometers, I think?
Yep. So in fact, that's a feature of James Webb. When it was launched with the mirrors intentionally misaligned. And so when we took the very first images, the reason is you want to align them all as one mirror. And you want to check the shape of each mirror. So when we launched it, they were slightly misaligned so that the image would show of a bright star would show, individual images for each mirror, and we could then analyze them to see if they were the correct shape. Because even though we measured on the ground that the mirrors were the correct shape, just in case, the mirrors are held by 3 points. And each of those points has a motor on it, so that we can move a mirror out or back or tilt it and tip it, but also one in the middle where we could pull it or push it to slightly change its shape. I mean, ever so slightly, but these mirrors are close to the correct shape, but we can tweak them just in case we made a mistake. And fortunately, all the mirrors showed that their stars in the correct shape, and we didn't have to tweak them. Then one by one, we steered the mirrors so that the image of that star would move to the center. And then we'd move the next one right to the center. And so one by one, we slowly aligned them all until they all overlapped right in the middle, using the other motors.
But it's a very large structure. How is it possible to achieve this precision?
It's a very large structure, but very, very stiff and thermally stable. Carbon fiber structure. I mean, we knew we could do that because Hubble also has a carbon fiber structure and optical bench. Now that said, we also know that over time, even though the carbon fiber was laid up and very carefully with low moisture and all of that, it's going to change over time. Moisture will come out, some organics will come out. And so it was anticipated that every 2 months we would have to go and readjust. Now so far it's been stable enough we haven't had to do very much adjustment. But probably twice a year, they'll measure some bright stars and tweak things just a little bit. Maybe this is funny, maybe not, but it's like a Swiss watch, right? I mean, Swiss watches are perfect. But every couple of years, you should take it in and have somebody make some small adjustment.
So I think it's fairly well known that there was an impact of a micrometeorite. Are there any statistics of micrometeorites, or is there data available of the attitude control as a consequence of those?
So we had a model for the micrometeorite environment at Earth-Sun L2, but virtually no measurements. And of course, around the Earth, it's unfair because so much of the micrometeorite environment is human-made. We have some measurements from the moon missions and from spacecraft that we've sent out in other places. We have some spacecraft where deliberately, we've measured the environment with little detectors where when the dust hits it, it creates a small signal. But very little data at L2. So we had a model. The model said about once every 5 years, the sunshade would get punctured. In fact, that's one of the reasons it has 5 layers. Because if we only had 1 layer and a micrometeorite goes through, then the sun would shine through and it could illuminate some of the telescope and warm up the telescope. So we have 5 layers, so it's very unlikely that it would go through all 5 layers in just the right angle that it would hit the telescope. So we launched the telescope and, right away one of the mirrors gets hit by something, relatively large. And so we actually can see the effect of that in the imaging. But it's not enough that it's going to hurt the observatory. And the first thing you think of is maybe our model is wrong. But since then, it's not been hit by something again. So we may have just gotten unlucky. But that will be a limiting, eventually, other things, can hit it.
I have the same question now regarding you during EVAs. Do you have in mind this could happen? What are the solutions? What can you do? I guess you have been prepared for that.
So an astronaut being hit by a micrometeorite, which could be a piece of paint, just micrograms, but traveling at 11 kilometers per second. So if a piece of paint comes off of some other vehicle, and it's not in the same orbit, our relative velocity, for the shuttle and a polar orbiter would be about 11 kilometers per second. And even a piece of paint hitting the cloth suit would create a tiny hole on the incoming side and a very large hole on the exit because it would immediately spall into. And that's the highest risk of spacewalks. If an astronaut wants insurance, Lloyd's of London will insure you for the launch and orbit and the landing, but no one will provide life insurance for spacewalks, not even Lloyd's of London, for any cost. So I worry about that when I'm here on Earth, but there's no point in worrying about it when you're actually doing a spacewalk. And it's actually a curiosity, because in low Earth orbit we have very good measurements of the debris, and it's ever increasing. It's a serious problem. And we thought that with the International Space Station and the number of spacewalks that we did to assemble it, that somebody would eventually get hit, within 10 years. So far we have nobody has been hurt, fortunately. So, but generally it would be very bad. Yeah, pretty much it would kill you.
So, well,
Just one small question.
Yeah.
So in principle, the James Webb can stay for the next 30 years or whatever. But do you have also doors there if you have to repair something, or can you improve?
don't go.
Oh, this is why I'm asking. But do you can improve James Webb after 10 years and put new cameras and like you did with Hubble, or it will remain 30 years as it is now?
It will remain as it is now. There was discussion very early on about making it serviceable, but partly I would say a lack of imagination. Well, it's 1 million miles from Earth. There's no point, and it's very expensive. So let me address the expensive part first. If you make an observatory where it's very easy to take instruments out and put them back in, you save a lot of money during assembly and test. And James Webb was built, like one of those wooden puzzles where there's only one way to put it together and one way to take it apart. And it was done so because of the thermal design. So they decided no servicing. It's 1 million miles away, nobody can get to it, and its lifetime is relatively short anyway. Well, we're lucky we have a long lifetime, but also the sunshade is very delicate once it's deployed. And so even having a spacecraft try and get near to it, if one of the little rockets goes, the sunshade would fold. So it's very hard to get near it. Of course, it's dark on the cold side, and it's cold. But I think in 10 years, I can envision a very capable robotic spacecraft, with a couple of arms that we could fly out there and could do servicing if it needed it. But nothing is designed for servicing. There's a very remote chance that we could refuel it. That's on the hot side of the spacecraft. So the fueling ports, we know where they are, that a robot could go and peel back the insulation and take off the caps and connect and refill it. But I think even that's extremely unlikely that we'll ever do. It would be expensive and risky. If the telescope is still operating, to go and refuel it. Fortunately, NASA's working on other space telescopes, as is Europe. So I think that's a better answer, is to build a bigger telescope. One of which that's in the conceptual phase now is the Habitable Worlds Observatory. So just at the very beginning, but it's planned to be about the size of James Webb, but in the visual and ultraviolet, so that it can study planets like Earth around sun-like stars. So 20 years from now, we should have the ability to see if there's any other Earths nearby, and whether they're inhabited, really. I think that'll be cool.
So I have a couple of questions on my
Yeah.
own. The first one, you show a slide with the service emission, and then there was a little sign, 2035, last mission to Hubble. Can you say a few more words?
Yes, the question, the obvious question is not how long will James Webb last. I think that has more certainty. Is how long will Hubble last? And for most of Hubble, it's been that electronics has been running so long that all the things that are going to fail right away have already failed and been replaced. So in principle, everything that's working should continue working other than a random failure maybe due to a micrometeorite or other thing. There are things that we know wear out. We have gyroscopes that are spinning at 70,000 RPM, very small ones, that we use to help orient the observatory from place to place very precisely. And they have a lifetime of a few years. So we put extras on board. We put 6, and we need 3. 3 have already died. It's been 14 years since we put them in. There are 3 left. One of them is kind of sick, getting old. And so at some point we're going to lose the gyroscopes. We can still operate the observatory. It just becomes less efficient because we won't be able to point so precisely. And Hubble is an observatory such that if you take a drinking straw and you hold it up at arm's length and look through that drinking straw, that's the size of Hubble's view. You see all those galaxies and you think, oh, Hubble must be a very wide-angle lens. It's an f/24. It's just a tiny, tiny patch of the sky. So when you move the observatory, you have to be close to where you want to look before you take your pictures. And the fine guidance sensors are the ones that help us get the exact position. But we have to be close enough that they can see the right stars. So the gyroscopes are going to fail eventually. And then we'll have to kind of, find roughly where we want to be and maybe spiral around a little bit. The fine guidance sensors have components, diodes, calibration diodes, that also age over time. And once we lose the fine guidance sensors, then we're kind of in trouble. There are a few odds and ends that are not working correctly. But Hubble was designed, for instance, computers. We have 2 computers. We have 2 computers for the spacecraft. We have 2 computers and data pipelines for the instruments. We have 2 power supplies. The motors all have 2 sides. And for many systems, we've lost one of those. And so we can switch over still, but reasonably confident that we'll be able to operate for another 5 years. I would say high confidence for another 5 years. Reasonably confident for another 10 years. At 15 years, Hubble will have gone low enough into the atmosphere that we won't be able to control it. And what determines that? The sun, the solar cycle. If the sun is very active, our atmosphere swells up, Hubble will come in quicker. Another thing that controls it is Hubble is now low enough that it's at the same altitude as Starlink satellites. So it could get hit by a Starlink satellite, and that's the end. Typically, Hubble would see a satellite trail go through its image once a year. And now it's once a month because of Starlink. Because Hubble does look towards at the horizon, but Hubble can look almost anywhere, just not near the sun or the Earth. But so there's Starlinks that are at a higher altitude, and it photobombs Hubble. So 2035 is kind of the time where either we have to let Hubble burn up in the atmosphere, or before that, send some mission back up. And there's hope that we decide to reboost it to 600 or 650 kilometers from 500. Even 550 would be good. 50 kilometers would give it another 10 years if it's still operating. And remember I told you in 2004 the NASA administrator canceled the Hubble mission? So one of the things I started was a robotic servicing mission. And the problem in 2004 is that the software to do the rendezvous and docking and the autonomous operations was not easy to develop. And now there are many companies that are developing robotic software, robotic spacecraft, private companies that are sending, small spacecraft, the size of this table, the volume of this table, with 2 robotic arms. And so I think for a commercial company, you could pay them. They would have to meet NASA requirements, but you could pay them to go up to Hubble, maybe do some simple servicing, like attach a new star tracker system that would allow it to do better pointing, and then reboost it by 100 kilometers, maybe for $100 million. That's very reasonable. Recently there was a SpaceX proposal, but when they presented it to NASA, it was very, very preliminary, let me say that. They didn't really understand how difficult it is. So.
Would such a mission be able to change a gyro?
So it turns out that star trackers have gotten so good now that we could put a wide-angle star tracker on the bottom, actually several, looking in different directions, and that would provide the same function as the gyros.
Really?
Yeah.
Okay.
If we can get Hubble to within an arc second,
Yes.
that's good enough for the fine guidance sensors.
It's a big step forward.
Yeah.
Shall we continue the conversation in front of some drinks outside?
Sure.
So, thank you so much again.